Okay, welcome to Strength Training Considerations Part 2, which is mechanical situation considerations. So some of the questions we have is this. When we perform free weights, we're assuming that they're going to transfer to normal training, right? To normal athletics. So question is, how well does free weight training transfer to ballistic movements found in sports, such as hitting someone in football or hockey or throwing a punch? And for those interested in strength and power, do free weights optimize force, velocity, and power across the entire range of movement? Well, let's talk about the master of mechanics, the greatest scientist to ever live, Isaac Newton. And Newton's second law states that acceleration increases as force increases and decreases as mass increases. So to maintain the same acceleration with a large mass, you need more force, and vice versa. Now, Newton's first law, which is the law of inertia, or law of motion, says how an object at rest will remain at rest, and an object in motion will remain in motion with the same magnitude and direction of velocity unless acted on by an unbalanced force. So we got this guy here checking the chick out, and he's like, man, I don't know if I can get this off the chest, right? So he's not able to produce an unbalanced force. So let's talk about velocity comparisons. Sport is reliant on high velocities, very high velocities. But with lifting constant free weights, we know that velocity is increased with decreasing load. So if you want high velocity, you got to decrease the load. All right? The problem with this is that you have lower force requirements. And that's something we got to think about. And also you decrease the duration of acceleration phase, which is not sport specific to ballistic movements. So you have high velocity, but now you take out the force, and then two, you accelerate a lower amount of time across the range of motion. So here's what I mean. If you have a 30% 1RM load, you have double the velocity, okay? However, you only accelerate 63% of the way through the lift. If we increase the load, basically, while my acceleration might decrease, the amount of time I'm accelerating increases. So the problem is, if I go heavier load, I accelerate along a longer range of the motion, which might be similar to a ballistic movement like a vertical jump. However, the velocity is totally different. But if I lower the load, the acceleration is only part of the range of motion, which is different than if I were to do a ballistic jumping movement. So we run into some problems. So here's the thing. Peak force produced is directly proportional to peak acceleration and mass. So we know that, right? But lighter loads have to be used to produce the desired acceleration, possibly reducing training specificity. So scientists got to find a method to have higher accelerations over a longer portion of the movement while having an adequate mass. Now, if also, as far as force is concerned in recruiting muscle, which is important for neural adaptations, if you look at AP, that's the acceleration phase, you can notice that during the acceleration phase, you have the most muscle activation in things like the deltoid and things like the triceps. But if you move to the deceleration phase, we see muscle activation is less. So muscle activation rises during the acceleration phase and lowers during the deceleration phase. So ideally, we keep the acceleration phase longer. And if we did, force should be longer. If you look here to compare normal weightlifting, the duration of time on a constant load, moderate intensity load, a constant load that's stopped, basically, is going to be 60% of the duration of the lift, right? But if we do a jump squat, for example, 96% of the lift you accelerate through. So this, again, we're trying to increase specificity, but this movement is lowering the specificity because we have a terminal endpoint, and therefore we have to decelerate. Finally, research suggests that adaptations in strength are specific to the load demands placed on an individual during a given lift. However, the load is limited by the mechanical disadvantage at the beginning or mid point of a given lift. So, for example, if you have a sticking point in the middle, as soon as you overcome the sticking point, you're just riding momentum. So your window of adaptation is from the bottom through the sticking point, and after that, you're just riding momentum. So what can we do? Well, one method we like is accommodating resistance. Basically, if you look, accommodating resistance is one of the methods that we use in our lab is bands, but chains work the same way, except it's a little bit different. Bands, for example, have minimal mass. Okay, so the minimal mass of a band at the beginning of the lift allows for a very high acceleration. However, as the band is stretched, it loads the bar with elastic energy, as opposed to mass. It loads the bar with elastic energy. So the acceleration early in the movement will have to be higher in order to compensate for the increasing load later on. So this is known as compensatory acceleration. So in other words, you have low mass in the beginning, but high elastic energy at the end. So you have to overcome that elastic energy with high velocity, high acceleration at the beginning. The same actually is true with chains, for example, except chains, the mechanism is some of the mass of the chain is unloaded on the ground. As you move up, the mass increases because it's moving off of the ground. So the mass is overloading the bar, whereas with the bands, it's actual elastic energy. But the concept is still similar. It's accommodating. So with accommodating resistance, acceleration lasts for a longer portion of the lift because you're compensating. Now, if we look here, if this is looking at knee angle, okay, and you're looking at variable resistance. So if you look at the knee angle in degrees, the early knee angle, 60 to 80 degrees, you don't see much difference in force. But when you move out to higher angles, where you adopt more of a mechanical advantage, now we see differences in force, to where the variable resistance, which is again like the added bands, produces greater force than the constant load. If we look at electromyography, if you look at 60 to 120 degrees, no difference. But when you move to the point where you have a mechanical advantage and are just riding momentum, when you add variable resistance, you have more muscle activation. Also, the endocrine response is higher. And in this study, decrements in force were greater, indicating greater neuromuscular stress. So we look at variable resistance, so 15 by 1 RM variable resistance, and then 5 by 10 with variable resistance, we see greater total testosterone. And if you look at the max constant and the hypertrophy constant, you don't see as great a testosterone response. So the endocrine response is greater, and also we have greater declines in force. Now what that means is when you're periodizing your split, you do have to take into account that you have a greater stressor on the system with variable versus constant resistance. So if you have greater stress, then you would think that this would lead to greater protein synthesis. Well, Walker and Holme actually, they presented this at a conference in Oslo a couple years ago. But basically what they found was if you look at P70, which remember is an important indicator of mTOR signaling and protein synthesis, variable resistance on the first week of training resulted in greater protein synthesis signaling than constant. Variables accommodating resistance, like where you add bands. But if you look at 16 weeks, there's no difference. So this suggests that if you don't periodize variable training, the response you end out accommodating to it. So think of this as a tool. You can't use the same variable resistance and the same technique every single workout or you will accommodate to it. But when it is novel, protein synthesis will be greater. So again, it's got to fit within a periodized split. So Jordan Joy, Ryan Lowry, and myself and all the guys in the lab, we performed a study in our basketball team. And we had one group, basically, they did a periodized training split, and once a week on their power days, we added bands. If you look, their lean mass gain was greater with the bands versus traditional. But also, variable resistance, which again, we use bands. If you look at the mean arrow, which is the red, they gained more strength on their squat than the control. In fact, the squat went up about 80 pounds with the bands and only 40 pounds in the control. So it made a big difference. If you look at rate of power development, more guys consistently increase the rate that they develop power in the bands or variable group than the control group. So we definitely found it worked. Now, what's the optimal load? We're unsure. We know that 15% of the weight as band tension has resulted in no change in strength or power. We know that greater than 20% does result in gains in strength and power. And we know that 35% is greater than 20% for the rate of force development, power, and force. So probably your sweet spot's about replacing 35% of your load with band tension, right? So if you're normally going to lift 100 pounds, right? So you might only do 65 pounds on the bar, and you're going to add band tension to where you actually end up having adding 45 pounds of band tension. So as far as how you apply the load, replacing 20 to 35% of your normal load of band tension has been efficacious. However, the study that I showed you that we did with Ryan Lowry and Jordan Joy, we found that we basically just added the bands to the normal load itself, right? So if you were doing 40 to 60% of your 1RM, okay, say it's 40 pounds, we might add 20% band tension to that. Okay, now the beginning of the load, you're fine, but you got to accelerate for the second half. So that's very important. We found that has worked as well. So you really have to play with what's going to work best for your sport. So in summary, bands should be used as a part of a periodized split if you want to keep using them to make gains. You should even likely periodize a form of accommodating resistance, but that hasn't been tested. We would assume that periodizing bands and chains would be optimal. Also, use greater than 20% of your normal load with bands also works. Thank you guys. I'll see you next time.